My hopes are that by now you're pretty knowledgeable about how to name ionic compounds and write the formulas from the names, how to recognize when the subscripts need to be reduced, how to use transition metals, and how to identify what Roman numeral would be needed to be written for a transition metal, and of course why. What we need to do now is add a whole other layer on top of that called polyatomic ions. Now, polyatomic ions are going to look a little confusing. They're going to sound a little confusing, but honestly, um, it isn't any more difficult. It just looks more difficult. Okay, so bear with me. A polyatomic ion is a single ion, meaning a charged molecule, but it's made of many atoms. Hence the name polyatomic, many atoms. Polyatomic ions. So they collectively, not individually, but they collectively are going to have a single charge. Now, a polyatomic ion is something that we are not going to break up, or we're not going to tease apart and look at each individual atom within a polyatomic ion. We are always going to keep them together and treat them as if they were kind of like as if they were one atom or basically one atom, even though it's a collection of atoms. But we're going to treat it as a single ion because they collectively are a single ion. So that is the theory and the concept behind a polyatomic ion. Let's get a little bit more into the practice. So like it says here on your notes, it says it's basically there are more than two elements and they are covalently bonded. So that's kind of interesting because they're going to be non-metals, but they are going to collectively, because they are an ion and they're charged, they're going to bond with a metal. So they're going to be charged. So you still have a giving and taking of electrons, still that electrostatic attraction from opposite charges. But instead of one metal, one non-metal, we're most often going to have one metal and a whole bunch of non-metals. But this is going to be positive. This is going to be negative, with one exception. Okay. Um, we're going to have to use parentheses sometimes, not like a transition metal, not because we don't know what their charge is. A polyatomic ion is always going to have the same charge, so we don't need parentheses to indicate what its particular charge is in a particular compound. We just need to do it in order to separate multiple subscripts. We don't want to put subscripts next to subscripts because then it looks like a larger number. So we need to put a parenthesis around to say, okay, how many polyatomic ions are there which have their own subscripts? Now, if you're saying, what the heck is he talking about? Don't worry, you'll see this in just one moment. Now, what we have here at the bottom is a list of some of the more common polyatomic ions. Now, sometimes a teacher would make you memorize these. We're not going to do that, but you do need to be very familiar with them and how to use them. So the first one you're going to see is called ammonium. What I want to point out with this one is it has a positive charge. This is the only polyatomic that has a positive charge. So because it has a positive charge, it will be the first thing within an ionic compound. Now remember, it's always going to be a positive negative, right? Positive negative. Well, in this particular case, you're going to have a polyatomic covalent compound with a positive charge collectively with another nonmetal. Now, why that's an ionic, because it's all nonmetals, that sounds confusing, is because it's an ion. NH4 is a +1 charge. So if it bonds with something with a negative charge, even though they're all nonmetals, it's still going to be an ionic bond caused by a positive and a negative. So that's a little bit weird. The next one we have is nitrate. Nitrate is an NO3. Now I want you guys to notice that this little charge right here, this little dash is of course a -1. So that's going to be a -1 charge. If you just see a negative, that's -1. That's a nitrate. Nitrite is the same thing, but with one less oxygen. So nitrate is NO3, nitrite is NO2. They both are going to have the exact same charge of -1. So these two kind of go together. We have the exact same pattern with sulfate and sulfite. Sulfate is SO4. If I take one less oxygen, it's SO3, and that's called sulfite. Both of them, again, have the exact same charge of -2. Okay? There's another one that's going to be similar to that. And like I said, there are more than these. These are just some of the more common ones. The next one we have is called acetate. Acetate is C2H3O2. There is another way of writing it, an alternate form, but all of that, even though that is actually 7 different atoms, 2 carbons, 3 hydrogens, 2 oxygens, all of them collectively have a -1 charge. So it is still an ion, even though that is 7 nonmetals. Okay, I know it's kind of weird, but you'll see how we use these in just a few moments. The next one we have is phosphate. Phosphate is PO4 with a -3 charge. Carbonate, CO3, all of that has a -2 charge or 2 minus. Again, remember that's the exact same thing. I'm using them interchangeably here. And then a one that you guys have all heard of and you guys like to sprinkle in randomly is something called hydroxide. Hydroxide is OH, and they together have a -1 charge. Now, like I said, you guys will never be pulling these apart and looking at the nitrogens separately from the oxygens. For nitrate and nitrite, they collectively have a -1 charge. Okay, so let's try this in actual compounds. Now, I do want to really quickly show you that you do have access to all these polyatomic ions. Here's your Google Classroom. If I open up this bottom one right here, it says Polyatomics, Solubility Rules, and Activity Series. What you guys will notice is that you have all of them right here. Again, you have access to this on every quiz and test. But notice there are many more than what we talked about. There's chromate, there's cyanide, dichromate, hydrogen carbonate, hypochlorite, perchlorate, permanganate, and I think we mentioned all the other ones. So notice there's many of them, but again, you don't really need to memorize these. You just need to be able to find them, and you need to be able to know how to use them. Earlier, I mentioned that acetate has 2 different forms. Here's the 2 different forms of acetate. If you add up the atoms, it's actually the exact same thing. It's just different ways of showing the same number of atoms. Both of these right here, again, have 2 carbons, 3 hydrogens, 2 oxygens. It just depends on which one you want to show. Regardless, again, a -1 charge. So those are all the polyatomic ions that we may use in class. Like I said, you don't really need to memorize them, although you actually may as we go throughout the semester and into the next semester. But you do definitely need to know where they are and, like I said, how to use them. All right, so let's again, like I said, do this in practice. Okay, so what we have here is the first example is magnesium nitrate. Now, magnesium nitrate, again, would basically be MgNO2, now, or NO3, Notice the parentheses. So the reason why that's the case is because magnesium is an alkali earth metal. It has a charge of 2. Nitrate is NO3. Oops, that's a 3. And all of that collectively has a -1 charge. So if I was to do my little crisscross method, this 2 goes down there, that 1 goes down there. And so what we end up with is MgNO3, 2. Now, the reason we need the parentheses is because what we don't want to do is we don't want it to look like this, MgNO3, 2. That would be confusing. It would look like magnesium NO32, and that's a compound that could never, ever, ever possibly form. So to prevent the confusion, we add parentheses to say that we have, for every 1 magnesium, we need 2 nitrates. Again, nitrate being NO3. Remember, the numbers on the bottom are the ratio of the atoms. So for every 1 magnesium, we would need 2 nitrates. So it's Mg, parentheses, NO3, parentheses, 2. Okay, another example we have right here on the right side of the screen is NH4,3N. Ooh, that's crazy. So ammonium, again, is NH4. It's the only positively charged. It has a +1 charge. And then nitride is just regular nitrogen. Again, not nitrate. Nitrate is on the left side. This is nitride. Nitride, again, from the periodic table, has a -3 charge because it's a group 5. So what I would do, again, using my crisscross, I would cross that down there, that down there. So what that means is I would have to write NH4, 3N. Now again, that looks really confusing because we don't want to say NH43N because again, there's no possible chance that we could have 2 nitrogens and 43 hydrogens, but what we can have is 3 ammoniums for every one nitride. Again, ammonium has 1 plus 1, it's going to lose 1 electron. Nitrogen has 3, so you need, of course, 3 ammoniums for every 1 nitride, right? Okay, let's try this again from scratch. All right, so what we have here is we have potassium carbonate. So potassium carbonate is K. K is a group 1 metal, so it's a +1. Carbonate is CO3, and again, it has carbonate right here has a carbonate has a -2 charge. See that right there, CO3, and above it is a 2-. So CO3 with a -2 charge. So CO3 with a -2 charge. Again, I'm going to go ahead and cross that down there, cross that down there. So my final answer is going to be K2CO3. Now notice I do not need a parentheses around the CO3. The reason I do not need a parentheses around my CO3 is because this number right here is only a 1. If that potassium had a charge of 2, I would need to do this. Although, if you remember that we reduce, if the potassium has a charge of 2 and the carbonate has charge of 2, those would then reduce. So I'm getting a little bit complicated. All I'm trying to say is if this here was a 3, let's say that's a +3, then I would need a parentheses around there, and I would put a 3 there after the CO3. It would be C2CO3 parentheses 3, but that again is just hypothetical. What we have is potassium with a charge of +1. Therefore, the final answer is K2CO3. That's it. Okay, that is potassium carbonate. All right, let's go over to the right side. What we have here is ZN3PO42. Again, that sounds like a mouthful. I know Zn is zinc. Okay. I know PO4. Again, if I look over here, PO4 is right down here at the bottom. PO4 with a -3 charge. So that is called phosphate. Okay. All right. So then again, just so you guys can see it, where all these numbers are coming from, that 3, if I go backwards, is a -3 charge, because again, we just saw that phosphate has a -3 charge, no surprise. And then zinc, if I put that 2 up here, the charge of zinc is +2. Now, do I really need to write the Roman numeral 2? In this particular case, no, because remember, zinc always has a charge of +2. Therefore, we don't really need to distinguish that fact. We could just say zinc phosphate, and anytime you write zinc phosphate in formula 4, the zinc has a charge of +2, the phosphate has a charge of -3, so it'd be Zn3 PO4 parentheses 2. That is the only form, the only possible form of zinc phosphate. The next one we have here is ammonium phosphate. So ammonium is NH4. Again, it's the only positively charged polyatomic. Phosphate, again, we just saw that one. It's PO4, and it has a -3 charge. All right, so let's go ahead and cross these charges. Some people say swap and drop. I kind of like that. I've never heard that before, but swap and drop or crisscross, however you want to say it. I'm going to go ahead and take those charges, move them down to the bottom. So now I have NH4. Notice I need to move a 3, so I am going to need a parentheses there. And then I'm going to have PO4, which is phosphate. I would put a 1 there, but again, a 1 is assumed. I don't need to write the 1, therefore I do not need the parentheses. So ammonium phosphate is NH4 parentheses 3, PO4. That is ammonium phosphate. Now, let me take a pause real quick and just remind you guys just how important it is to be able to correctly name ionics. As you guys can see, this is a little confusing. And when we get into the future chapters in this class, if you're not able to identify ammonium phosphate as NH4 parentheses 3 PO4, you're going to be in a world of hurt, because you must be able to figure that out in order to find the mass, in order to do stoichiometry, in order to do solutions, in order to do predict products of reactions. So many things in the future are going to hinge on your ability to write the formulas of these ionics. given ammonium phosphate, you need to know it's NH4 parentheses 3 PO4. Okay, there's no way around that. All right, moving on. That's my little soapbox, but again, I cannot overstress that fact. All right, what we have here is silver, or excuse me, I almost said the answer. Ag2SO4. So Ag is silver. SO4 is sulfate. Again, if I uncrisscross the charges, I would have a parentheses there. That 1 goes there. It's not the 4, because remember that 4 belongs to sulfate, right? If you take that 4 away from the sulfate, it's no longer sulfate. SO4 is sulfate. You cannot take that 4 away from it. So the charge of silver is +1. The 2 right here comes from the charge of sulfate, which is a -2 charge. Again, you're not sure about that. Double check right here. Sulfate, notice right there, SO4 with a -2 charge at the very bottom right there. So that is, in fact, correct. So the charge of silver is, in fact, 1. But again, do we need to write the charge of silver? No, we don't, because just like zinc, it's always going to be a +1. Zinc is always going to be a +2. So those are the exceptions to the transition metal rule. The next one we have is CuNO3. So Cu is copper. NO3 is nitrate. All right, so we know it's copper nitrate. Copper is a transition metal, and it does require a Roman numeral. Remember, the only two metals, transition metals, that do not require a Roman numeral are zinc and silver, which we just did those two examples. So copper definitely is going to need one. In order to figure out what it's going to be, typically, again, as you hopefully know by now, it would be the number out here at the very end, not the 3, because the 3 belongs to the NO3. It's the number after the 3. Now, I don't see a number, so I may have to go back and look at my, my little formula chart here. So nitrate, if you look kind of in the middle of the page, it's NO3 with a minus charge. NO3 with a -1. You guys see that right there? NO3 with a -1 charge. Therefore, that tells me that the nitrate has a charge of, -1. So guess what? Because there is no numbers, that means the copper must also be a +1. Because again, copper must be 1, because if you didn't see it, it would be reduced, because you cannot reduce a 1 any further since the nitrate has a 1. If copper was anything other than 1, you would see it after the nitrate. For example, if the copper charge was 2, it would be Cu NO3 parentheses 2. If the charge of copper was 3, it'd be Cu open parentheses NO3 close parentheses 3. But the fact that there is nothing after the NO3 tells me the charge of the copper must be equal to the charge of the nitrate, which in this case is a 1. All right, so hopefully your head's not hurting. Let's go ahead and push forward. So what we have here is PbSO4. Pb is lead. SO4 is sulfate. Again, lead is underneath the staircase. It does require a Roman numeral. Let's go ahead and check from the chart. Sulfate, down here at the very bottom, notice the -2 charge. SO4 with a -2 charge. Interesting. So if it's a -2, again, what I should see is a Roman numeral 2, right, like that. A Roman numeral, excuse me. Oh, I'm sorry, that's not correct. What I should see is a 2 right there, because the charge of sulfate is -2. So the fact that I don't see anything there tells me that it must have been reduced, and the charge of lead sulfate, or lead in this particular compound, is a 2. Because if the sulfate is a -2, and there is no numbers at the bottom, then they must be equal to each other. Therefore, using reasoning, the lead must have also been a charge of 2. So lead 2 sulfate is just PbSO4. Again, if lead was anything other than 2, then you would see the 2 of the sulfate, and then there would be a number possibly after the SO4 outside of the parentheses. Okay, here's another example. Chromium 2 nitrate. Chromium is Cr. Nitrite is NO2. Let's just double check. Again, if we're not sure, we have this to look at. Nitrite, NO2 with a -1 charge, with a -1. Okay, then again, it tells us right here the chromium charge is +2. It's much easier to go this way because they're giving you the charge of the chromium. It's +2. All we need to do is crisscross or swap and drop. And in this case, we're going to have CrNO2 parentheses 2. Sorry, that's a little sloppy. CrNO2 parentheses 2. That's the only way you could write chromium 2 nitrite. All right, calcium hydroxide. Calcium is Ca. Hydroxide is OH with a -1 charge. So calcium is a group 2 metal. So it's a Ca with +2 charge. I'm going to move that down there, move this down here. So what our final answer is going to be Ca1, or don't write it, OH, move the 2 down right there. Okay, that is not the same thing as CaOH2. This one is correct. This one is completely wrong. CaOH2 means you have 1 calcium, 1 oxygen, 2 hydrogens. The correct one is 1 calcium, 2 oxygens, and 2 hydrogens. So we need those parentheses to say we have 2 hydroxides, not just 2 hydrogens. So please be careful with that, okay? That's going to, again, really be important in the near future. All right, the next one we have mercury 2 acetate. Mercury is Hg. Its charge is +2 because, again, they just told us that. Acetate is C2H3O2 with a -1 charge. Again, I'm going to go ahead and move this down here, that down there. My final answer is Hg1, C2H3O2 parentheses 2. Antimony, which is Sb, hydroxide, OH, with a -1 charge. Again, they tell us right here the charge of antimony is +5. Therefore, again, if I crisscross or swap and drop, this goes down there, that goes down there. Final answer, Sb1, or don't write it because, again, it's assumed, OH parentheses 5. That's antimony 5 hydroxide. All right, guys, so we just covered the polyatomic ions. I showed you where to access them. You guys know where to find them. You guys know how to use them. We're going to require a lot of practice to get this under our belts, and I understand. So again, practice makes perfect. If you guys have any questions, please do not hesitate to ask. And as always, thank you guys for watching.